Hello, everybody. My name is Jase Gault, and I will be presenting the effect of a gate valve on pipe flow. This is my computational fluid dynamics final project for this semester at Lamar University. So first, I wanted to get into what is computational fluid dynamics, or CFD for short. As defined by ANSYS, which is a company that actually has the computational fluid dynamics program I ran my problem in. Computational fluid dynamics is the science of using computers to predict liquid and gas flows based on the governing equations of conservation of mass, momentum, and energy. How can CFD be used? CFD is used mainly in areas like aerospace and defense, the automotive industry, healthcare, new energy, for the example of modeling full hydrogen chains, and pipe flow modeling, which is what I'm doing here. It can be used in aerospace and defense to help model planes and rockets or prototypes that they want to create. It is very often used in the defense industry to model their weapons like rockets and stuff like that to make sure they have the maximum efficiency. In the automotive industry, it can be helped to show airflow over a vehicle and ensure that it is streamlined and as aerodynamic as possible, really. And then in healthcare, it's actually being used nowadays to help model certain systems that are more complex, like airways. Now people are using it to model airways to metal breath throw that you don't have to actually take a lot of scans of a person's throat, but instead you can have a model that you can kind of edit there and kind of work along with. So now we're going to get into the problem that I'm working with today. My problem will be analyzed at multiple points, 25%, 50%, 75%, and 100% open. One thing you'll notice in this video is I actually didn't analyze it 100% open because for the reason that 100% open is zero turbulence. It's going to have zero turbulence and it's going to have streamlined velocity. So I can say I'm analyzing it, but we know from the laws of fluid dynamics that it will be a streamlined flow because I'm not using anything like a pipe roughness or erosion to kind of create those disturbances. So here on my problem on the right, I have basically 2 feet of tube with a 12-inch diameter. Right now it's showing the 25% open system. Water comes in from the left and flows out from the right. My goal is to see the area of turbulence and how they relate to the velocity and pressure. This is just a diagram of a gate valve in case you haven't seen one before. What the part we really need to focus on is the difference between closed and open, how that bar comes down. That bar will be cranked up to 75%, 50%, and 25% for the purposes of this video. Next, I want to talk about the meshing. This was the meshing for my first simulation. This was the most refined one I could get. I tried to refine them later on in the next steps, but every time I would try to refine it or I would work on the edge sizing, it would actually crash, so I wasn't able to run the simulation. And then I did finally get it to work one time, but it took 3 days to get to about 57%, and I figured that that might be a little bit too fine, and then I just need to run it at this because it's the only way it would work on my computer. So this is the meshing. This basically determines where the points that's going to be analyzed the heaviest. This is the pressure contour that I got after running my simulation. Like I said, water is going to flow in at 20 meters per second. This shows the pressure that happens after, I think it was around 90 seconds. So after 90 seconds, this is how it works after it evens out from flowing. This is a velocity animation. This is one of the only animations I could get. I attempted to record animations for 50 and 75%, but for some reason, every time I tried to run them, my laptop would crash the program. So I was only able to get contour images, but this video does help show us how they form in the later videos, so they kind of apply to all the same things. This is the video right here. As you can see for the velocity, it starts off swirling up and swirling in. That's kind of what we'll see in a little bit with the turbulence. But as you notice, after it gets about halfway through the video, it streamlines and it runs along the bottom, which is kind of expected of this flow. And as you notice, there's a bit of a slow area up the top because the high velocity water all goes through. Next, I want to show you the turbulent kinetic energy for 25% opening. Like I said, it'll kind of flow similar to the velocity, but one thing you'll notice, which I kind of thought was different, I figured that most of the turbulence would come from the bottom of the pipe, but I learned that actually that big opening has the most turbulence because that water is not moving at such a fast, streamlined rate, which when I think about it after seeing these videos, it does make sense that the streamlined flow would be mostly running in line with one another, so the turbulence would occur where the flow is not streamlined and flowing slower. This is the meshing for 50% open. As you can tell, I actually changed the model a little bit. I wanted to add a little more pipe in the back. I think I did add an additional 2 feet. That way you could kind of get a better idea of what the turbulent energy looks like after it hits the gate valve, because I noticed there was a lot missing from that first simulation. So on my second time, I added to it to make it better. This is the pressure contour. As you can tell, it's the same one as 25% basically, maybe just a little less pressure under the gate valve now. The area before the gate valve is still under high pressure, and after the gate valve is still low pressure. You can see at the end how it starts to lighten up. That's because as it goes down, that pressure will eventually even out, and I made it just long enough so where you can actually see it start to even out. This is the velocity contour. This one had colors that I've actually never seen before on ANSYS, but it's because it was such a broad spectrum of velocities. So as you can tell, it's coming in at about 20 meters per second. And I did actually do calculations to try to prove at least that the velocity is flowing faster through the gate valve. They weren't exact, but you can't get exact on a 2D simulation of a 3D pipe. They are off, but it does show that the area times the velocity of the entrance is lesser than around the same as the area times the velocity of that gate valve. They weren't completely accurate, but they were pretty similar. And as you can tell, again, it goes through streamlined flow. This time there's just a larger area of streamlined flow. This is the turbulent kinetic energy for 50% opening. As you can tell, it goes down, and the blue mimics exactly the high-speed velocity is where the low kinetic energy is, which is expected. That's exactly what happened in the previous one, but that swirl moved further back due to the gate valve being opened more. The swirl moves further back. Next, I'm going to talk about 75% meshing. All the meshings are almost the same, except for the fact that the gate valve goes up and I had to change the numbers there. All of these meshings were done with edge sizing. I did not use any bias because I felt every part of this square every part being analyzed was as important as the other. And for the record, for all of these simulations like pressure contour, I did use the residuals to be 1e -6 to make sure they were precise, because I wanted my readings to be as precise as they could be since I couldn't get the meshing to work properly. This is the pressure contour for 75% opening. As you can tell, since that gate valve is opening more, the pressure is lessening, or there's a much smaller area of low pressure, and the high pressure side has lower pressure than it initially did. And as you can see, you can really see that area on the far right now where it's starting to lighten up and return back to normal. This is the velocity contour for 75% opening. It's almost similar to the other ones, except this area of streamlined flow for high velocity is significantly larger. And again, that blue area will be where the turbulent kinetic energy is. As we can see in this slide, as it starts to drift off to where the parts where the swirls won't be flowing in streamline anymore, they're kind of curling up, and that is right where all that turbulent kinetic energy is. That is all I have for my presentation. Thank you for watching. If anyone has any questions, please feel free to reach out and contact me. Thank you.